Hi, this is Baird Givens, and in this video, I want to talk about an example of how we compute the interior and closure of a set. And for this example, we're going to use the lower limit topology so that we really have to think about our definitions of closure and interior. Before we start, let's just remember that in the lower limit topology, the basic open sets have the form of an interval from A to B, where the lower limit A is included and the upper limit B is not included. So those are the basic open sets in the lower limit topology. And then we can also remember that in general, the interior of a set U is the largest open set contained in U. And the closure of a set U is the smallest closed set containing U as a subset. Okay, so the interior is kind of like inside U, as big as it can be and still open. And the closure is around U, it contains U, and it's as small as it can be and closed. Another important thing that we've learned is that if I want to think about a particular point, and I want to know if a particular point is in the interior or the closure, I can say a point Y is in the interior of U if and only if there is an open set U such that Y is in U and U, oh, sorry, I used the letter U twice. That's terrible. There is an open set, let's say V, such that Y is in V, which is a subset of U. Another way to say that is that U is a neighborhood of Y. Okay. And then secondly, Y is in the closure of U if and only if for all open sets V containing Y, V intersect U is not empty. Okay, so these are going to be the ideas that we've already learned about interior and closure that we can use to solve this problem. All right, so let's go ahead and work on the problem now. So we have part A is I'm looking at the set capital A is the interval from 0 to 1, including 0, but not including 1. Let's first think about the interior. So first I might think, what is the largest open set contained in A? What is the largest open set contained in A? Well, if I look at A has the form of basic open sets in this topology. So A is open. So since A is open, the largest open set inside of it is itself. So the interior of A is A. All right, so what we're using there is that if a set is open, then its interior is equal to itself. Now, what about the closure? I might try to think about if A is closed, but I don't know right off the top of my head if A is closed. I could figure it out, but it's not like where I just looked at A and could see that it was a basic open set. So let's just think about it a little bit more. Let's think about A looking like the interval from 0 to 1, including 0 and not including 1. And let's use this characterization of the closure as if I want to look at a particular point, this is what I want to think about. Okay. And again, I also want to think about the closure as meaning I know that the closure contains every point of A, but it might contain additional points as well. So I want to look at points that are not in A and think about whether I need to add them. So for example, what if I think about a point below 0 down here? If I think about a point below 0, does every open set that contains that point touch A? No, I could just make an open set kind of very small around it, and it wouldn't touch A, right? What about if I look off to the right? What if I look at, like the number 2, for example? Does every open set that contains 2 have to touch A? No, I can draw an open set around 2 that does not touch A at all. The only other sort of special point I really want to think hard about is right at the number 1. Can I find an open set that contains 1 and does not touch A? Or is it true that every open set that contains 1 touches A? So I think if I make my open set be the open set that goes from 1 to something a little higher, so if my open set starts at 1, then that open set contains 1, but does not touch A. So that tells me that 1 is not in the closure. 1 is not in the closure. So I don't need to add anything to the closure here. The points below 0 are not in the closure. The points above 1 are not in the closure. 1 itself is not in the closure. So there's nothing to add. So in this case, the closure of A is A. Now the next example. Let's look at B. I'm going to move these just a little bit out of my way, just a little bit. Okay. So let's look at part B. Capital B is the interval 0, 1, including both 0 and 1. So what is the interior of B? The interior of B. So for the interior, we usually want to sort of imagine maybe either taking the set itself or maybe removing some points from the set. So let's think about the points that are in the set and whether or not we need to remove any of them. And for the interior, we want to think about, can we find an open set V that is entirely contained in B for each of these points? So for example, if I look at a point in the middle between 0 and 1, I can find an open set that's entirely contained in B. So that tells me those points in the middle are in the interior. What about 0? Can you find an open set, which means, or could mean a set of this form, an open set that contains 0 and is still contained entirely inside of B? Yeah, I think I could just go from 0 up a little bit, and that would be contained inside of B. So that tells me that 0 is in the interior. And then finally, what about 1? If I take an open set that contains the number 1, I claim that as soon as it contains the number 1, it also has to contain a little bit above 1. And so any open set that I try to put containing the point 1 is going to have also some points above 1. So I can't squeeze an open set there inside of B and still have it have 1 in it. So 1 is not in the interior. So the interior of B, I want to include 0. I want to include all the points between 0 and 1, but not 1. Now for the closure of B, I'm going to do a similar sort of thing as what I did for part A. Here's B again. And for the closure, you think about, are there any points outside of B that I need to add to get the closure? Are there any points outside of B that I need to add to get the closure? Well, I know that the points below 0, I can certainly, any point below 0, I can find an open set around it that doesn't touch B. And any point above 1, I can find an open set around it that doesn't touch B. So I don't see any points that I need to add. And so the closure of B is 0, 1. And then finally, the third set is the interval from 0 to 1, not including 0, but including 1. So for the interior, I'll think about points that are in the set. Take points in the set. For each point in the set, can I find a neighborhood of that point that stays inside of C? Certainly for points in the middle, I can draw basic open sets around them that stay inside of C. But just like with part B, I cannot get 1 in the set. As soon as I try to get 1 in a basic open set, that basic open set's going to stick out a little above 1. And so 1 is not in the interior. Every other point is. So the interior of C is the interval from 0 to 1, not including either endpoint. And then the closure of C, let me draw C again. The closure of C, I have to think about what do I need to add to C to get the closure. Okay, so I might need to add things that are not already in C. Certainly points above 1, like way up here, I can draw open intervals that avoid C. So those points above 1 are not in the closure. And points below 0, those are also not in the closure. So really the only point I have a question about is 0 itself. If I have a basic open set that contains 0, then I claim that a little bit of it has to stick out above 0. I have to go a little bit to the right of 0. And so any open set that contains 0 will have to touch C. Any open set that contains 0 will have to touch C. And so therefore 0 is in the closure. And so the closure of C is the closed interval, including 0 and including 1. Okay. And maybe over here, just to make it more clear, I just wrote A there, but let me just write these first consistency. So this would be 0, 1, including 0, but not 1. And this would be 0, 1, including 0, but not 1. Just so I'm writing them all in the same format. All right, so I found the interior and the closure of all of these sets. There's some sort of interesting things to see here, some sort of interesting observations we can make. So first of all, on part A, it turns out that the interior of A is equal to A, which is equal to the closure of A. So that's a thing that can happen, okay? That tells me that A is open because it equals its own interior, and also that A is closed because it equals its own closure. And so A is a set that is both open and closed. And that often bothers people because the words open and closed in English kind of feel like opposites. But in topology, you can definitely have a set that is both open and closed. You can have sets that are open, sets that are closed, sets that are both, and sets that are neither. So this A is both open and closed. For B, we have that B is equal to its own closure. B is equal to its own closure, but it's not equal to its own interior. So that tells me that B is closed but not open. And then C, for C, we actually have an example where the interior of C is a subset which is not equal to C itself, which is a subset and not equal to the closure of C. So C is neither open nor closed. And C is an example of a set where the interior is a proper subset and the closure is a proper superset. So you can have all kinds of different situations that can come up. Sometimes the interior and closure are equal. Sometimes they equal the set you started with. Sometimes they're not. Okay? So that is an example of how we use the theorems about interior and closure to actually figure out what the interior and closure are, especially in an unusual, for us, topology. Thanks for listening.